Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is the new episode of the Turbulence at the exascale podcast. For those not familiar with the podcast, the aim is to gather the view of the community regarding exascale computing for turbulence and what are the challenges and opportunities about exascale computing for turbulence research. This podcast is part of the ExCALIBUR initiative in the UK. This is an initiative led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. And its aim is to deliver research and innovative algorithm development to harness the power of exascale computing. This podcast is also linked with the UK Turbulence Consortium. And I'm very pleased to say that today we have two guests for the price of one. We have Professor Spencer Sherwin and Chris Cantwell from the Department of Aeronautics. So they are my colleagues who are working in the same department. They are both experts in computational fluid dynamics and high performance computing, and they are the main developers of the flow solver called Nectar Plus, and they will have the opportunity to talk about this amazing flow solver. So good morning, Spencer and Chris.
Morning.
Morning.
I'm very happy to have you in this podcast, and without more talks from me, we are going to start, and I'm going to start with Spencer. So for those who are not very familiar with you or who don't know you, please can you tell us about yourself, where you're from and what you have studied, and how did you end up in the Department of Aeronautics at Imperial College?
Okay, well, I first came to the Department of Aeronautics at Imperial College as an undergraduate. So I studied a long time ago, an undergraduate. I did manage to leave for a little bit when I went to the US. I went to Princeton to study my PhD. And that's where I guess we started the interest in the code and the spectral element type technology. At the end of my PhD, I had got married actually, but I got married to somebody from the UK, and we decided to come back to the UK. And I was kind of fortunate enough to get a position back in the aeronautics department. So I've only really gone to two places. So I've gone back to the States and come back here, and I've been in the department ever since.
Thank you, Spencer. And same questions for you, Chris.
Yep. So I'm originally from Liverpool. You might be able to still sense a bit of the accent there. And yeah, I did my undergraduate degree in maths at the University of Warwick. And then I really liked Warwick a lot, so I stayed there to do an MSc and a PhD in scientific computing at a kind of recently started Centre for Scientific Computing there. And then after that, there was a project at Imperial about electrophysiology, which seems a bit of a change from the fluid dynamics that I was doing at Warwick, but it was an interesting numerical challenge, I guess. So I came to Imperial as a postdoc back in 2009 to start working on that project. And then basically I've been at Imperial since.
Great. Thank you both. Let me start, Spencer, by asking you, how did you become interested in computing, high performance computing and for the study of turbulent flows?
So that would have been during my PhD studies when I went to the States. I worked with a guy called George Kaniadakis, and he was very interested in spectral element methods and unsteady and turbulent flows at the time. My PhD ended up evolving into trying to develop techniques for unstructured regions. At the time, mainly they were just sort of quadrilateral or hexahedral based technologies. And so that's where the HPC or the computational science started. And in those very early days, they did actually, in the US at Princeton, have a parallel computer, one called a Hypercube. So right from the beginning of my PhD education, there was access to HPC facilities. When I came back to the UK, there was just about the start of HPC computing beginning in the UK. We had a machine by Fujitsu that didn't have a queuing system at the time, but soon after that we started having a centralized HPC facility, and it's just kind of grown from that those early days.
Great, thank you. And Chris, I guess same questions. How did you become interested in high performance computing?
Yeah, so I mean, I guess I've kind of always had an interest in computers back from when I got my first computer aged 8. I think I taught myself programming in school, But it was only really, I guess, when I was in my final years of my undergrad where I had the opportunity to do some kind of applied maths courses. And there was a course on topics in scientific computing that I took that I think that really got my interest. And I did a final year project on comparing the performance of FFTs, which, well, Fourier transforms at least, which sounds a bit dull maybe now when I talk about it, but ultimately it was actually a very interesting. I found the, you know, the computational aspects and the algorithmic aspects and the performance side of things. So I guess that really perked my interest, if you like. And then I went on, and obviously the opportunity came up to do the MSc PhD. And obviously it kind of built on there. So I did my PhD with Dwight Barclay in Warwick, and that was where I got exposed to a lot of the fluid dynamics and that side of things. But also, you know, through the Centre for Scientific Computing, I also was exposed to a lot of HPC, and we had their own cluster. And in fact, my office was literally right next to the computer room. There was a window where I could look on the computer where I was running the jobs. That was kind of, if you like, inspiring in a way, but
very good.
But yeah, but I guess that was how I developed my interest, and then it's
Great.
obviously grown from there.
Great, thank you. So the reason why you are both invited at the same time is that you are working on the same flow solver called Nectar Plus. So now I'm going to ask you, Spencer. So can you tell us more about Nectar Plus? For those who are not familiar with Nectar Plus, can you tell us more about the capabilities and how it was designed and everything?
Yeah, I got a similar pattern of my career when we go through this conversation. I'm always starting back in my PhD days. So as I mentioned, my PhD was in developing this unstructured version of these spectral element techniques. At the time, there was a structured version called Prism of this code that another student called Ron Henderson of George Kaniadakis has developed. So I first started, when I wrote my code, took that prism and added a T because we had triangles, and I called it Trism. So then, but that wasn't very acceptable as a name. And my supervisor, who's Greek, came up with the name Nectar. So that's kind of where that started from. There was also another code called Necton at the time, which kind of bore similar heritage. So then for the next 10 years, we kind of developed this Nectar package, but a lot of it was just to do with the fundamentals and development of the algorithms. And by 10 years into that, my PhD-ware code had just become really too complicated and hard to manage for anyone except for me. So I guess it was way back in 2003 to 2005 that we decided we should be rewriting the code. And that's where the plus comes from. So the Nectar evolved into Nectar Plus, us trying to have a more software engineered code with a bit of structure to it. And that started very heavily with my close collaborator at the University of Utah, Mike Kirby, who comes more from a computational science background and able to inject that. And then from that, we quite soon afterwards, I'm not exactly sure what date, Chris and another senior developer or team leader, Dave Moxley, joined us. And they kind of brought their experience of software engineering into place. So that's kind of where the evolution of Nectar Plus has come from. I needed to do that because I wanted people to use these codes more. And in order to do that, we needed to be able to give away the code to make them do useful features. So we started a lot with incompressible flows and stability analysis. That was a lot of our early works. We kind of had a variety of discretizations, not just 2D, but so-called 2.5D, where you have a Fourier extension. That's a very popular use of the package. And in the intervening time, we've also evolved it to fully three-dimensional type flows. Now for both incompressible, which was where we started, and the more recent developments have been incompressible flows. And maybe Chris will talk about this in a moment. Along the lines, we also have been involved in various biomedical or biological type flow applications, which are predominantly incompressible and compressible, and there's some additional work that Chris might comment on.
Great, thank you, Spencer. I have a small follow-up questions. What's the difference between NEC 5000 and Nectar Plus?
So NEC 5000 is originally Necton, that was Paul Fisher, where there was a few main authors. He's the main ones carried on. So Necton evolved into NEC 5000. NEC 5000 is a hex or quad-based code. I guess Nectar Plus is allows for all element shapes. So in that sense is geometrically a bit more flexible. I guess we have invested more recently in compressible as well as incompressible, although I think NEC 5000 is also going in that direction. But so the main distinction would be hex-based versus unstructured type shapes.
Great, thank you. Now a question for you, Chris. So you've joined Imperial College and you started being one of the main developer of Nectar Plus. So can you tell us more about your experience as one of the main developer of Nectar Plus?
Yeah, so I mean, I guess there's four of us, right? That are sort of the overarching. I mean, we call ourselves the project leaders, I suppose now. So basically, our role is more to kind of steer the project, both from the kind of scientific side, but also the software engineering side. Of course, many of the people that are contributing to the project maybe don't have they don't have a lot of experience maybe on the software engineering side, although they might be very good at the scientific side. So some of what we do is to try and steer the development to make sure that the additions that they're providing to the code are kind of maybe more general or fit in with the framework in a kind of more usable and robust way. It's very easy to write a code that solves a particular algorithm, but then to do that kind of in a, if you like, a robust way is a bit more challenging, and so that's kind of part of our role. I mean, I guess as part of what Dave and I have contributed to the project, we've sort of instilled this more rigorous software development lifecycle kind of principles. So we've, I mean, I think when I joined, we were using CVS as our version control system, and we moved from that to Subversion, which came with some improvements, I think, in terms of the branching and that. And then when Dave arrived, we moved over to Git. So we've had this kind of transitioning through the version control systems, and now we have a whole kind of GitLab setup, which is providing us with a whole set of development tools, if you like, to strengthen our software in that respect. So a lot of what we contribute as our main developers, if you like, are to do things like code reviewing and steering that and managing those kind of merge requests and on our issues as well as the kind of distribution of the code and packaging it up, things like that. One final aspect, I guess, that we sort of try and steer is the pedagogical aspect. So trying to make sure that we have tutorials and things that allow people to utilize our code, and I think that's particularly important in terms of getting impact from our code and everything. So and getting other people to use it. So trying to strengthen that is a particularly important aspect, I think, for us.
Thank you. Thank you. So you're both main developer of the code, but you are also using it to study a wide range of fluid flow, and even more for you, Chris. We'll talk about that. So Spencer, what type of flow you are studying at the moment with Nectar Plus?
Yeah. I think over the last 5-10 years, I've tried to focus a lot more in the application in the industry side of it. So earlier in my career, and I'm talking about there was a previous 20 years, it was more on sort of fundamental science and more academic problems. So currently we're working with three industries. We're working with COMAC, the Chinese civil aircraft manufacturer, and for them we're looking at boundary layer transition and boundary layer transition modeling. For a long time, I've worked with McLaren, both the racing team and the automotive. And in that case, we try to apply it to their very challenging external complex geometry flows. That's potentially some of the most challenging flows we have to do in terms of industrial level complexity. And more recently, over the last 3 or 4 years, we've been working more and more with Rolls-Royce. And of course, they have a lot of turbo machinery and compressible flow types applications. So we've been looking at turbine blade simulations and more recently at sort of intake shockwave boundary layer type interaction problems.
And the same question for you, Chris. What are you doing with Nectar Plus? So
yeah, so we do have an ongoing EPSRC grant looking at the formation of leading edge vortices over wings in unsteady flow. So that's one of the projects we've got going at the moment. So that kind of leverages both some of the kind of fundamental stability analysis that I kind of grew up with, if you like, during my PhD. So we're applying that to try and understand the mechanisms about how these leading edge vortices form, but we're also utilizing kind of full-blown large-scale DNS simulations in order to compare with experimental data as well, and kind of validate what we're seeing with the stability analysis, validate that at the, with full-scale DNS and the experiments. So this project is collaborative. It's also with the University of Bath. So we have Professor Gersel there doing experiments on these types of geometries and looking at the formation of these vortices, and then we're able to compare them quite amazingly well, actually, with our DNS results. So yeah, we've also got an EU project looking at reduction in jet noise, so doing some jet installation noise. So we're looking at particularly what happens when you take the jet and you actually install it under the wing, and the effects of that on the noise produced. So part of that project is mainly to demonstrate the capabilities of our high order methods to be able to kind of solve these high Struhel number flows. But another aspect of it is to deal with the kind of IO aspects of these kind of large scale simulations, which is maybe one of the more challenging things we can talk about later. I guess we've already mentioned that there's some biomedical aspects. So a lot of what I've done since coming to Imperial has been around the electrophysiology area. So you might argue that's not really a flow simulation. Some people might call it electrical flow, but it's essentially looking at the propagation of electrical waves over the heart. And these electrical waves govern how your heart contracts. And there are obviously certain medical conditions like arrhythmias that form, particularly with old age or with disease, that can cause arrhythmias that then obviously are not very good for people's lives. So we're looking to try and use the modeling in order to try and steer the treatment of those diseases and help clinicians treat people better and have better success rates. So there's some modeling activity going on there that builds on Nectar Plus, but in a slightly different way to the compressible and incompressible flows that we've talked about already.
Great, thank you very much. Let's talk now about exascale computing and the transition to exascale computing. So I have a question for you, Spencer. Would you say that Nectar Plus is ready for the transition to exascale, and what effort are you doing in this direction?
Yeah, always difficult to say you're definitely ready, like you can push a button and everything's going to work. I wouldn't want to go that far, but certainly we've been looking to embrace what we can in this area as things have been evolving. And I would say there's various challenges we face. An earlier challenge has just been straightforward I/O. Even when we're going for a larger number of cores, when we handle these very complex geometry cases, how do we do the pre-partitioning, loading up and putting it back out? And so we've transitioned from what was a sort of an XML, rather long-winded format into HDF5 format to be able to address that. And that's definitely been necessary for us even to get on and run stuff. Similarly, of course, we need to make better use of accelerator units. And so we've been working more recently on adding better vectorization, and that has all sorts of impacts about our memory layouts and our internal strategies. And we have a range of solvers, and so we have to mix and match which solver we want to use. Now, because of the memory bandwidth challenges that come with the exascale, we're looking to move to more and more matrix-free type algorithms versus historically under the previous architectures, we've used a lot more matrix type structures. So all of those elements are kind of going on under the hood. They've got to various levels of maturity. I suppose our definition of whether we've achieved it is whether we get it into our master branch. The IO stuff is in the master branch. The vectorization stuff is nearly in the master branch. And we'll see about the matrix free and the preconditioning. That's still really kind of in the development branches at this stage. So we're very mindful of it, and we're getting close, but I wouldn't like to say we're fully there yet.
Great, thank you. And Chris, I have a very specific question. I know you have been doing a lot of work on fault tolerance on supercomputers. So can you tell us more about this aspect of your research?
Yeah, so this kind of stemmed out of another EU project that we had a few years ago that was basically there was a section on looking at fault tolerance, and I found that was particularly interesting, I would say, and possibly a major hurdle to exascale if we kind of continue on our current trajectory. So I mean, I guess at the moment, you know, where most codes are probably built around, you know, parallel systems such as the likes of MPI, and the kind of default behavior if one of those processes dies due to, you know, for instance, a node failure, is that your whole simulation aborts. And while we sort of maybe tolerate that at the moment at petascale, because those failures are relatively infrequent and our simulations are maybe not too big compared to exascale, I think when we get to exascale, it's going to become more and more of a bottleneck to us getting throughput on these systems. So the kind of objective of the fault tolerance is to, instead of kind of accepting failure, or rather instead of just having failures and having to rerun stuff, is to kind of accept that the failures are going to happen and try and mitigate that in software. So rather than you know, the MPI process aborting and your simulation stopping, is we're trying to see if we can utilize some relatively new extensions that are being proposed for the MPI standard, this user level failure mitigation, in order to try and essentially handle that in Nectar Plus or in whichever solver you're talking about, okay? So instead of it failing, you would instead either spawn a new process on another node, or instead maybe utilize spare processes. And the idea is that in that way you can keep the simulation going and hopefully improve the overall energy efficiency of your simulation. Now, of course, I started off doing a kind of prototype implementation of these ideas in Nectar Plus, but of course, it would be better to have a more broader usage. So I'm in the process of trying to develop a kind of standalone, if you like, resilience layer that would sit between MPI and your application code. And the idea is that any kind of time-dependent solver type code should be able to leverage this, because it basically works by intercepting MPI calls when you're setting up your solver. And then that enables it to replay those communications, if you like, when a spare process takes over from a failed process, allowing that to quickly get back up to speed, if you like. And then we use the traditional checkpointing methodology, but through a kind of remote memory checkpointing in order to handle, you know, the progression of the simulation as it's integrated in time. So yeah, I'm hoping to get that to a more, if you like, production ready state, and then test it on a few other codes as well, besides Nectar Plus.
Great, thank you. That's very, very interesting. So Spencer, I have another question for you. If tomorrow you get access to an exascale supercomputers, what would you do with it? I mean, higher Reynolds number, more complexity, more accuracy? In which direction you think we will go when we will have access to exascale computing?
All of those type of things, but I think if I'm going to make an observation in my own career, we're now, even with a petascale resource, at the border of being able to do industrially relevant type flows. So there may be the simpler industrially relevant flows. So we're at the bottom end, we're able to get to the right Reynolds numbers and compare pretty well with some experiments on what the experimentalists might consider as their least challenging problems. So what we're seeing, we can potentially open up to the greater, higher Reynolds number, higher speed flows, more complex geometries. So it's kind of unleashing that potential into more industrial practice. And I think that's what the exascale kind of represents for us. We're there on the border, they can see it happening. It's not quite got the codes in the right place. If we get them more robust and we've got that compute capability, then you'll find them using them more and more, and hopefully benefiting at least the advanced engineering type design practices that require high fidelity type CFD. That's where I think we're going to unleash.
And so you're heavily involved in the UK Turbulence Consortium. So I wanted to ask you a more broader question. Do you think the UK community for studying turbulent flow is ready for the transition to exascale computing, or do you think that we still have a lot of software development work to do?
There's always more to do. I suppose as a community, our strength and weakness is that we have lots of people, sometimes we have a lot of codes, But the advantage of that, we have a lot of people that know how to write and adapt those codes. So I wouldn't like to say all of the codes are ready, but the kind of knowledge base as a community is there to be able to evolve and sort of tackle whatever challenges we're going to face by depending on which sort of exascale compute comes along and what the problems with things like memory bandwidth and RIO. So of course, we have our lead codes in the sort of flagship codes in the UKTC, and they're potentially the ones that are better supported and probably most ready. But behind them, there are a bunch of other codes that I think can be adapted reasonably well, but it's going to require a bit of software engineering effort to make sure they're kind of fully utilizing these new facilities.
Great. Another question for you, Chris. I know you have been working a lot on fault tolerance, which might become an issue on exascale computer. But I wanted to ask you, what do you think are the challenges associated with using efficiently exascale computing for to study turbulent flows, so in CFD? So fault tolerance is one. We briefly mentioned IOs, but is there any other particular issues you think are going to be problematic?
I mean, I certainly think IO is going to be a major concern. Partly related to that is the idea of how we visualize our results, and maybe we're going to have to transition from being less dependent on writing out our simulation data and visualizing it as a post-processing activity, and maybe focusing more on using in situ visualization to manage the sheer volume of data that these kinds of simulations are going to produce. So that's probably the area that I think we maybe need to develop more. And I know a lot has already been done in this, certainly in some of the codes that are out there. Maybe we haven't quite got there with Nectar yet. We have some kind of provisional sort of semi in situ visualization kind of techniques, but I think that's certainly an area that we can develop a bit more.
Great. Spencer, a quick question about, we didn't talk about meshing. Is meshing a problem in Nectar Plus? And while we are talking about meshing, can you say a few words about, there is a working group part of the ExCALIBUR project on meshing, I believe. So if you can, a few words about meshing.
No, I mean, so there are two aspects. One, there is a broad scope of are the meshing techniques we have fit for the next scale of simulations. If you take commercial codes that might need billions of cells, and how do we prepare ourselves for that? Chris was just mentioning the IO challenges. Can we afford just to load up something that large, or do we need to actually do mesh generation a bit more in situ? Perhaps not on an exascale level of computers, but at least at the petascale level to be able to run these simulations. But if that's to be done dynamically, then we need to be able to access the CAD and the meshing techniques within these environments. And that technology just isn't that mature. So that can be a massive bottleneck. I mean, so that's for the standard meshing techniques. We also have a slightly different headache that we have high order meshing in our Nectar Plus. So generally we leverage traditional or commercial type meshing softwares, and we make relatively coarse elements that we then want to deform, and that deformation to represent the geometry correctly adds different sort of headaches to the algorithms and the robustness of the meshing techniques. So there's an area called high order meshing these days, which also is needing to mature and come on board. We have certain advantages in that we don't need so fine meshes. Maybe we don't need billions. We could get away with millions or hundreds of millions, and then we use these polynomial techniques. But we need to do a lot more interrogation and correction of the sort of meshes to make them valid before we can even run anything. So that's the main focus of the Element project, of trying to identify what the bottlenecks and challenges are for running industrial complex geometry flows on these sort of systems.
Great, thank you. A question for you, Chris. So are you happy with, I mean, it's a tricky question. Are you happy with the hardware that are currently available to do your research, or is there you can foresee any issues in the future? I mean, we mentioned bandwidth, memory, but are you happy where high performance computing is heading? And if there is anything you can change, what would that be?
Yeah, I mean, I think we've kind of talked about the I/O and the data movement, and I think that really is going to be one of the major bottlenecks going forward. I mean, we all kind of know that the CPU performance is far outstripping the advancements in the memory technology, and certainly to I/O systems as well. So I think that's going to ultimately become the bottleneck, and that's probably where we need the biggest developments in order to try and overcome that. I mean, the fault tolerance, I obviously believe there's potentially an issue in the fault tolerance side of things, but even if it's not down to component failure completely, ultimately components can degrade, and if you end up with, you know, one component or one node that's running slower than all the others, that will potentially slow down, you know, the rest of the system. So in that sense, the fault tolerance can step in and maybe take that node out of the equation, if you like. So yeah, I think data movement is probably the biggest thing that I would like to see improvements in. I don't know really how we overcome that, though, given the laws of physics and everything. So I'll leave that to people with more expertise in that area. But yeah, I would say data movement is the biggest concern for me.
Great, thank you. I have one final question for you both. It's the same question. I'm going to start with Spencer. What are you going to do in 10 years or in 15 years? Where do you think on the long term, so beyond exascale computing?
I get to retire on that time frame.
You get to retire.
Well, I don't know. Academics never retire fully, but I guess my ambition within that time frame is to see these sort of techniques that I've invested all my life into actually apply not just to our own code base, but out there in industry sort of practice. So when we achieve that, then I suppose I'll have to redefine my focus and mission. But I think we've probably got another 10 or 15 years of this before that fully happens. Good.
And same question for you, Chris. So I guess you're a bit younger, so you have a bit more time. So you will not retire, yeah, but
I'm probably not going to retire. Well, I hope not. Anyway, yeah. I mean, I think seeing some of the techniques that we're really, you know, kind of fighting to get working now, and that becoming common practice would be good. I mean, I guess on the biomedical side, you know, being able to simulate kind of whole hearts in real time for me is kind of a holy grail, because I think at that point you're really at the point where you can influence patient care and things like that. But I realize that's maybe a bit off the topic of the turbulence side of things. But yeah, I think being able to, you know, simulate these large scale simulations just as a kind of run of the mill type of thing is what we're going to see in the next 10 years at least. So.
Great. Thank you both for your time and for your input. I think it was really nice talking to you and to learn more about Nectar Plus and about your research. So we wish you all the best, of course, for your future endeavor. And the recording of this podcast will be made available on YouTube, on SoundCloud. All the links are on the UK Turbulence Consortium website. And you can also follow us on Twitter. It's UK Turbulence in one word as well, where we will put some updates about new episodes. So thank you, Spencer. Thank you, Chris. And for everyone, that's all for today. And I hope to see you soon for a new episode of the podcast. Thank you very much.
Okay, thank you.